Okay, good morning. We should be live. I hope you can hear me, and I hope you can see this slide. So just give me a thumbs up when you can, so I know that you're all receiving the live stream. As I uh, as I mentioned earlier, if you have any questions about this strike situation we might be in starting tomorrow, keep an eye out on the pages of UMSA, which I'm sure is going to address this, and I'm sure it will be in the news as well. As soon as I know more about a potential end of the strike, then of course we will also be able to communicate that. Um, so, on to the material for today. We're going to be talking about the last bit of chapter 9 about linear momentum and collisions. In particular, we're going to talk about collisions in multiple dimensions briefly, and then move on to center of mass, and hopefully at the end we can do something that's slightly a fun application in rocket propulsion. So, we've talked about collisions and the strategy of solving the problems in one dimension. So if a problem is phrased and it involves a closed system, momentum, linear momentum is conserved. So that is our first equation that we are going to use. Um, and then we're going to identify here in step 3 whether kinetic energy is conserved. That's the case for elastic collisions. And if kinetic energy is constant before and after the collision, then we'll be able to write down a second equation. So we've got two equations in two unknowns. The two unknowns are generally the final velocities of the two particles, for example, that have interacted. So two equations and two unknowns, which we can, of course, solve using regular linear systems and systems of equations. So now we're going to look at that in multiple dimensions. So now we're going to have a total initial momentum that has x, y, and potentially z components. Actually, if we go into into quantum mechanical systems, there's often 4 momentum vectors, so they have 4 components. So in each of the components, the momentum will have to be conserved independently. So in this case here, if we have a final momentum that's along this direction, we have 2 components or 2 vectors, 2 particles in the initial state that kind of stick together to form that final momentum, then the 2 initial momentum vectors will have to add up to the final momentum vector, which means that the y components will have to add up to the y component of the final momentum, and the x components will have to add up independently as well. So the x components will have to add up to the x component of the final momentum. So even in the case of multiple dimensions, the same thing is true, that in multiple dimensions that the initial the total momentum initial will have to be equal to the total momentum final, and that means now that p total initial x component will have to be equal to p total final x component. Same thing for the y component, and same thing for the z component. So the momenta have to be conserved independently for each of the coordinates, for each of the directions. So we can use that now to our advantage. And then actually one way in which we immediately could use this to our advantage, since the direction and the coordinate system that we pick here is somewhat arbitrary, oftentimes we'll pick the coordinate system such that the initial or the final total momentum is along a fixed direction, so that, in this case, for example, if the final momentum is entirely along, if there's only one vector here, we could have easily picked that to be the x-axis and written everything in terms of that x-axis, which simplifies the math a little bit, in particular because it means that for the other component, the y component here, it would have meant that the initial components of the y momentum would have to be opposite, so they add up to 0, which is the final momentum in the y direction. So we applied that last time already a little bit to the example of a car and a truck colliding. So we're not going to go over that again. Let's look at a different example here, though, which is, and this is the same strategy, so let's skip that, which is the explosion of a scuba tank. So this is an example where we have an object. This is the first example of an explosion, actually, that we look at. This is an object that breaks apart into 3 different parts with 3 different masses. So let's say we know the initial mass of the scuba tank, and we know the 2 pieces. You know, 2 pieces. 1 piece is 7 pounds, for example, and the 1 piece is 10 pounds. So we don't know the mass of the 3rd piece, for example, but we know the angles at which 2 of these pieces flew off. So what's then the mass of that 3rd piece, and what's the velocity with which it flies off? That could be a question that we might ask, and this is one of the examples in the textbook. So let's start off with the first part here, which is what is the mass of the 3rd piece? Well, that's the easy part because that's just scalar quantities, right? So we have the total mass of the initial scuba tank, 31.7 pounds. We have the mass of 2 of the parts, 7 pounds, 10 pounds. So the remaining mass will have to be for the 3rd piece. So that 3rd piece will have to be then 31.7 pounds minus the mass for 1 piece minus the mass for the other piece. And that will give us a mass of, in this case, we'd have to do the math here quickly. So let's do the scuba tank explosion. We're just going to write this down in symbols, symbolically here. So we have that the mass, the total mass, or in other words, this is essentially the initial mass, is mass 1 plus mass 2 plus mass 3 plus mass 3. So we can solve this for the unknown mass. So that's the easy part. Now we also want to, however, determine the velocity of the 3rd piece. And we know the directions at which the first 2 pieces went off. So piece 1 went off in the horizontal direction. Again, in some sense, we can always pick the direction in which piece 1 flew off. We can pick that to be the x-axis. We don't have to necessarily make this the horizontal direction. In this case, the problem here just uses the horizontal direction, so it probably doesn't have to explain why we can choose the coordinate system that way. But since we have freedom to choose the coordinate system that way, we can choose the x-axis to be along one of the pieces to make the math simpler. In particular, P1 will now not have a y component at all. P2 flew off at an angle theta with respect to the first piece. So this is going to have a y component to the momentum. Part 3, which is what we want to calculate the initial velocity of, that flew off at an angle theta. An angle phi with respect to the x-axis. And of course, we can already approximately say that if 2 pieces fly off in this direction, in the positive, mostly positive x direction, then the 3rd piece will have to fly off into the negative x direction. And why is that the case? Because we know that the total momentum of those 3 pieces will have to be equal to the total momentum of the scuba tank before explosion, which is a total momentum of 0, right? Everything's at rest, so whatever mass this has, the product of mass times velocity will be 0. So P total initial is equal to m times v initial, and that's equal to 0. that means that P total final, which is P1 plus P2 plus P3, will have to be 0 as well. So now we can write this down into the different components, and rather than writing this down in on the whiteboard here, I just made sure to copy the formulas. So our final x component has to be equal to our initial x component, and the final y component of the total momentum has to be equal to the initial y component of the momentum. So that means that the x components of the three pieces added together have to be equal to the x component of the initial momentum, which is 0. Or if we put this all together, we have the mass times velocity in the x direction, and that gives us ultimately the momentum for piece 3 in the x direction in terms of the masses and the components of the velocity in the x direction for the other pieces, piece 1 and piece 2. In the y direction, the same thing applies, and obviously this is nearly identical, this expression. So here the final momentum in the y direction is the sum of the final momenta in the y direction for each of the three individual pieces. So that's the products of the masses and the velocities. We can solve that for the final momentum for the third piece, which will be given by minus the sum of the momenta in the other direction. So now the last part, of course, is what is, for example, m1 times v1y. m1 times v1y. Oops, I wanted to go to this figure. m1 times v1y. Well, v1y is 0 because p1 is entirely along the x direction. So this term will be 0. m2 times v2y will be m2, which is a mass we know, times v2y, so the y component of the v2 velocity of part 2. Oops, wrong direction. So that will be the sine of theta times the velocity with which part 2 flies off. And then in the x direction we can do the same thing, except now we'll have v1, the x component of v1 will be just the entire v1, because the entire v1 is along the x direction. And the x component of v2 will be v2 times the cosine of this angle theta. So what we end up with is an expression here where p3 of x is minus m1 times v1 minus m2 times v2 times the cosine of theta. And here the first term drops out and we end up with minus m2 times v2 times the sine of theta. So all of that, of course, serves to then calculate the x component and the y component of this of the momentum of the third particle, of the third mass. So if we then find m3 p3x and m3 p3 what am I writing here, m3 v3 y, so we can find both of those, which will then give us, if we calculate m3 from our first part, that will give us v3 of x, v3 of y, and from that we can find the angle phi, which will be the inverse tangent of v3 y over v3 x. So all of that from conservation of momentum in this explosion scenario, just based on the fact that we know the velocities and the masses of two pieces, we can calculate the velocity, the mass, and the direction, of course, since that's included as part of the vector nature of velocity of that third component. Now, one thing you'll immediately realize is that if the sum of the total velocities of P1 and P2 are larger, then the momentum and the velocity of P3 will become larger. If the mass of part 2 is much lighter than the mass of part 3, then the angle for P2 will be larger than the angle for P3. So again, it's just a matter of conservation of momentum in all of the three coordinates x and y, and of course in this case we're not using z, but it would be a similar problem if we had a z component. It would just add more math. It would add another equation to our system here, but ultimately we would add one more equation, but we'd get additional information on the velocity. So okay, so that's all I wanted to cover in terms of collisions in multiple dimensions. It's really just the same as collisions in one dimension, except multiple times, right? Once for the x direction, once for the y direction, once for the z direction, if that occurs. One of the benefits is, again, that you can choose the direction of the coordinate system, and that often allows you to simplify the problem. So let's move on now to the next topic, which is center of mass calculations. And before I go into too much detail on these drawings here, let me outline some of the math behind center of mass calculations. So really what we start from here is a collection of masses, a collection of particles that are interacting with each other. So there's forces between those particles, and maybe they're actually, they might be repulsive forces, there might be attractive forces. It doesn't necessarily matter. There are internal forces, and the internal force on particle J, the net internal force on particle J, we'll write as little f internal subscript J. So that's the mass, that's the net internal force, on particle J. There's also going to be potentially a net external force, that's what we're going to call F external J. That's the net external force on particle J. So on J, there's going to be two forces. There's, let's say this is F internal on J, and then there's some net external force, which we're going to draw in red here. So those are the forces on particle J. So that means now that if we write the motion of particle J, the change in momentum of particle J over time will be the total force on particle J. So that's going to be the internal force on particle J plus the external force on particle J. That will describe the time derivative of the momentum, right? That's our equation of motion, which is that the force causes this change in momentum for particle J. So at this point, we're just looking at this as still a large collection of particles. One thing we're going to need next now is, of course, to turn that back into equations. So we're going to actually use, we're going to turn the momentum back into velocities and into time derivatives of velocities. So we're actually going to introduce, we're going to need to introduce the masses so we can get from momentum back to positions. So in that case, we're going to write mj is, of course, the mass of particle J. So that means that we can also introduce total mass m, which is the sum of mj. So that is the total mass of entire collection of particles. So if we're talking now about the total mass, now we're going to also want to talk about the total force on this collection of particles. The total external, or the total force on all of the particles, or the net force on all of the particles will be what we call big F net. So that's going to be the total force on all of those particles, both internal and external forces. If we add all of that up, we'll get a sum that goes over the internal forces and a sum that goes over the external forces. Now here's where the magic happens in some sense. So if we think about this first term here, the sum over the internal forces, if we look back at our drawing here, we're summing this over all of the particles, and for each of the particles there will be a component that's included in one direction and a component in the other direction. So when I'm going over the particles here, for one particle I'll have a component to the internal forces that is pointing in one direction, and there must be then, because it's an internal force, there must be another particle that has the equal and opposite force applied. So for each of the forces included in the internal forces, there will be an equal and opposite component that is also included. So this must be equal to 0. Or in other words, the total internal force, the total net internal force must be 0. Because all of those Newton's third law force pairs cancel each other. So if we write our net force as the sum over all of those forces, we can also write it by now using this equation, right? We can write it as the sum over all of our time derivatives of the momenta for particle J. So the net force is also equal to the sum over J of dpj dt. So the net force on the collection of particles will also be equal to the sum over all of the momenta, all of the time derivatives of the momenta of this collection. And this now is equal to the sum of only the external forces over all of the particles J. And that's what we're actually going to call not F net, but we're going to call this now F external, because now we know that the net force is actually the external force, because all of the internal forces are canceling out. They're just mutually, they're just components in there that mutually cancel out between each other. So that means that now we're at the point where we have that the net force is equal to the external force, and that's equal to the total sum of the changes in the momenta for each of the individual components. So F external is the sum over I of dp over j dpj dt. So what we've done here is for our collection of particles where there's internal and external forces, we've been able to write down how the momenta of those particles change based on the external forces only. The internal forces do not affect how those particles move with respect to each other in this sum. So that's something that that allows us, of course, to simplify things. So now we're going to take this a step further. So now we're going to write this mass, this external force. That's what we could write with or Newton's second law as mass times acceleration, where this is now the acceleration of the entire collection of particles in some sense, which we'll define here in a minute. So that's the acceleration of the collection, not the individual particles. And so we're going to want to introduce something. We're going to want to define this a little bit better. How do we define what it is that is accelerating in this collection? What is the position, and what is the velocity that gives us that acceleration, for example? So to do that, we're going to introduce, we're going to rewrite this a little bit in terms of the velocities and the positions of those individual momenta. So if we write m times acceleration, that's now m is equal to the sum over j of mj times acceleration, and that's equal to the sum over j of dpj dt, or the sum over j of mass j times dv or drj dt. And that's actually equal to the time derivative of the sum over mj rj. Right? I feel like I'm missing something here. No, I did miss something here. This should still have been a v, so it's the derivative of the velocity, and then here this would have been vj, so that's ddt of the sum over j mj dr dt, and so all of that becomes the second derivative d2 dt squared of the sum over all j's mj times rj. So what that means is if we put this and this together, it means that the acceleration is of a vector. A is the vector d2 dt squared, the sum over j mj rj, divided by the sum over j of mj. So let's take a step back. What we did here is we started from a collection of particles with both internal and external forces applying on it. When we have the internal and external forces, the internal forces don't play a role when we add up everything in a net force that applies on the entire collection of particles. That's where the sum over the internal forces canceled out to zero. That net force, or in other words, the external force, can be written as the mass times some acceleration, as long as we define the acceleration to be of this form. And if we define the acceleration of this form, then of course we are going to be able to assign a position to that, and we're going to call this position the center of mass position, which is what's in the parentheses here. So the center of mass position is the sum over j mj rj divided by the sum over j of mj itself. So this is the center of mass position for this set of particles, and with that center of mass position we can calculate an acceleration, and of course we can also calculate a center of mass velocity, which is going to be ddt of our center of mass. So we can calculate a velocity and an acceleration such that that acceleration now satisfies that the external force is equal to the mass times the acceleration on that object. So this center of mass position essentially takes over from the positions of the individual particles if all we want to describe is the overall behavior of the collection of particles. And we can, of course, in this case, we have a sum over individual particles. If we do this for continuous distributions, continuous distributions of mass, then we'll find that our Cm is now the integral of the position times little bits of mass divided by the integral over the little bits of mass separately, and of course this part here will be the mass itself, just like in this case that was the total mass of the collection of particles. So if we want to calculate the center of mass, what we will do from any reference point, we'll calculate the weighted sum of the masses of the particles multiplied with their positions. So here we have m1 times r1 plus m2 times r2 plus m3 times r3. If we add those three products together, we'll end up with a vector which we then normalize with the mass itself, and we'll find the position of the center of mass. So in this case, the center of mass ends up being, the equivalent would have been here. So that means that probably M1 and M2 are heavier than M3, which we can tell also because M3 times R3 is shorter than R3 is drawn here, and it's shorter than M1 times R2, M1 times R1, so M1 R1 weighs more in that average. So this is for three particles. One example where we're going to use this is, for example, the center of mass of the Earth and the Sun, or in this case, the center of the mass of the Earth and the Moon. So we have the mass of the Earth, which we can think of as being concentrated at the center of the Earth. We can have the mass of the Moon concentrated at the center of the Moon. The center of mass with respect to the origin point here inside the center of the Earth is going to be the given by the expression here. So the weighted sum of the position of the Earth, the position of the Moon divided by the sum of their masses. And as it turns out, you can calculate this. It's done in the textbook as well. When you calculate this, you find that the position of the center of mass of the Earth-Moon system is actually underneath the surface of the Earth, which just means that the Earth has a much larger component in this weighted sum, and so it pulls the center of mass so close to the center of the Earth that it's actually inside the Earth. So that was right, and I did talk about the continuous distribution. So we can do this for continuous distributions as well, but because this involves integrals, and for half of you, this is probably something that would require maybe a little bit more calculus before we can get into that. So let's skip the integrals here. We've already done we've already done some math that I hope has not tired you out. So then the last bit I wanted to talk about, I don't think we have time for that. So do read this chapter on rocket propulsion. Again, it relies on integrals because it involves thinking about how the mass of the rocket changes as the gases are emitted. So every time when an amount dmg of gas is emitted by the rocket, the mass of the rocket itself changes by dmg, or by minus dmg. So that changes some of the equations here, and that causes some logarithms to appear because of integrals. So read that section, but I don't think that will be something we're going to focus on for the midterm, for the final anyway. Okay, that was it for today. So I hope to see you all again soon, but unfortunately, I do not know exactly when that will be, and for now at least, it looks like it won't be on Wednesday, and we'll see from there.